Hello, everyone. Thank you for joining and welcome to the next episode of Deep Dives with WinRiver technical experts. It is a great pleasure for me to be here with you today. My name is Andrei Holodny and I'm a principal technologist at WinRiver Technology Office. I'm also a company representative at the ROS2 Technical Steering Committee and the co-chair of the ROS2 Real-Time Working Group. Robots and ROS2 in particular is a hot topic today. ROS2 applications were mostly developed by academia and startups for research and development purposes. Now, we can see that more and more companies deploy ROS2-based solutions in various industries. What problems are they facing and how these problems can be solved? This is the topic of my talk today. I will briefly talk about the history of ROS, challenges while ROS2 deployment and how Yocto Linux can help with it. I will also show a demo to illustrate what I have covered in the first part of my talk. If you have any questions after my talk, you can reach me out on GitHub, ROS Discourse or LinkedIn. So let's begin. To illustrate my words, I have put here some numbers to show how fast robotic industry grows on the example of the service robots where ROS2 plays a significant role. A rapid proliferation in robotic capabilities driven by innovation in machine learning, artificial intelligence, adaptive computing, 5G and vision systems is causing the market to nearly triple in value. And if you map this and look to the ROS2 metrics, which were published last year by Open Robotics, we don't have these numbers for 2021. You could see that in the year-to-year comparison, that the total number of packages is increased by more than 50%, and the downloads by nearly 90%, visitors by 63%. So you see here a tremendous growth in ROS2 value and how people use it. But what is ROS and ROS2 in particular? So ROS is a robot operating system, is a framework for writing robotic software, and it is a collection of tools, libraries to simplify creation of complex robot applications. And it is licensed, it is open source and licensed under BSD. It has started by Willow Garage in 2007, and it went through different stages. I have just put some probably highlights here. So in 2013, ROS Industrial Consortium has started, and they have provided a different packages for industrial applications. Then important to mention that in 2015 ROS2 release was published, and ROS2 is a successor of ROS, so it brings some capabilities, better real-time, possible safety certification, and they are still running in parallel, so ROS and ROS2, but in the future, so there are more and more now users switch to ROS2, and in the future, so ROS2 will replace ROS. So I have started working on this on ROS in 2017, where I have ported ROS2 on VxWorks. It was also interesting because I have seen a great potential to run ROS2 on real-time operating system. And now in year 2021, we see that there are two releases, one for ROS2, which is galactic, and one for ROS, which is noetic. And this work continues. ROS2 community has decided to create various interest groups, so under umbrella of the ROS2 Technical Steering Committee. And one of the groups which I'm part of as a ROS2 real-time working group, and there are different company members there. You can see the list here. And these groups were created to actually to improve various ROS2 capabilities. And this working group, ROS2 real-time working group, deal with a reference ROS2 real-time reference system. So apparently to improve real-time capabilities and provides guidelines and creates benchmarks to test ROS2 system and improve ROS2 real-time behavior. So really everything around real-time and ROS, because we see a great potential in the ROS2 being implemented for real-time. And you can visit our community webpage, and we have different projects, and look and participate into that. Let us look at ROS2 stack. So as a developer, you would develop ROS2 applications. And for that, you would use the complete stack underneath. And if we look at this at more details, we will see that even so you can use a different hardware. At the moment, ARM 64 and Intel the supported platforms. So you would use even if it is called ROS, so robot operating system, you need operating system because ROS2 is a middleware. So and there are multiple operating systems for your choice. Most popular is Ubuntu Linux, where you it is a tier 1 operating system for the ROS2 community. Then you might use various DDS, so data distributed services, middleware providers. You have multiple choices here, depending on your needs. Then another two components are components which come from ROS2 community and included in the ROS2 releases. So depending on your application needs, you might use control, navigation, move it frameworks on top of your on top of ROS core to develop your applications. So development workflow is very I would say it's very modern and use all these components which already exist. So basically, I would like to mention that it is a native development. So you develop on the platform for this particular platform. So you would use, as I have mentioned, Ubuntu. Then you would use ROS2 packages which are built for Ubuntu, and then you would use a Git and IDE of your choice, VS Code or whatever other IDE, and you would probably develop even using code spaces in Git, in GitHub, and you would develop your package, so your application. Then you would you need to create some probably some CI/CD pipeline to build your package and validate your package. And you would use to build your package, you would use a callcon which comes with ROS, and then you would use whether GitHub Actions or Travis or Jenkins to validate your package. And this is still not integrated as a as a package. It's just it will be like a bunch of binaries and other artifacts. So you might try to integrate it into release, and then you need to create a release distribution, so release of your package, and then it will be automatically catched by the and add to the ROS distro, and then Bloom as a release tool of ROS would then add your package to the set of other ROS2 packages, and then it will be added and accessible for other developers. So this is basically how the process looks like. It is, I would say, it's very good for prototyping because you can make use of rich and flourish ROS2 ecosystem. You have many available packages. It's easy, extensible. You have a community support with all these available examples and so on. So it's really like a very quick start, and you can develop your package and test it. However, what happens if you need to your system is not Intel system, or you need to tune your works, to tune your system for the footprint or for the performance. And about this, we will talk in the next slides. As I have mentioned, if you then, the next step would be productization. So if you would, even if you would still use Ubuntu and you would still use Intel as your target system, which would control your robot, you might have a problem to tune this system for performance, for footprint, for check for software provenance, and some other stuff. So and the reason for that is that it is a binary distribution. It's quite difficult to modify, and one of the solutions to solve this problem would be to switch to another Linux distribution, which is called Yocto Linux. What is Yocto Linux? Yocto project is open community-based project. First of all, it was created more than 10 years ago. It's not a distribution, but it's a set of tools and sources which allows you to create a custom distribution of your choice. It's most used embedded Linux in industry. It uses cross-development approach in compared to the desktop where you develop natively. That means that you can use one platform and develop on this platform for another platform. It has, I would say, it's very similar approach or very similar idea as ROS2 has. It means that each package is described in the form of metadata. So you have for ROS2, you have a package file where it is described what version, what are dependencies, and so on. So in Yocto Linux, it is the same approach. You define all of this information, or you in form of recipes. So it's also kind of it's a metadata approach, and it's highly configurable. So you can really can tune your system for and squeeze it and tune for performance, for the footprint pretty easily, because it's like it's embedded distribution and it is dedicated for the low-end devices, and it has a commercial support. And WinDriva Linux is one of the commercial providers for the Yocto, and it has a good support for ROS2. So there is a Meta ROS layer, a Yocto layer, which people can use to build inside their distribution ROS2 applications. I have put here a table with some differences between Yocto Linux and the desktop Linux. As you might see, so I would say major differences are that in compared to the desktop Linux, where you get ready-to-use binary packages, and these packages are quite difficult to modify. You have in Yocto Linux, you have a source distribution where you can easily, and you have a recipes which allows you to easily include, exclude, and modify dependencies of those packages. Then another difference is that you have a cross-compilation model versus native model. That means that you need to have a host, so one computer where you compile your distribution for another computer. You have much broader silicon vendor support by Yocto Linux in compared to desktop Linux. For the desktop Linux, for instance, for Ubuntu, you have basically generic Intel and generic ARM support, where for the silicon, so for the Yocto Linux, almost each silicon vendor provides for their boards these meta layers for Yocto, and then it's quite easy to include those layers and produce image, so Linux image for this particular board. So it has a very similar approach, I would say, for the build system. So it has a build tool in ROS2. It called Colcon. In Yocto, it is called BitBake. And what you are basically doing, so what this tool is doing, it just reads your metadata information and then compile this bunch of packages based on, in one case, on ROS distro information, and in the Yocto case on the meta layers information. So as I have said, it's quite difficult to tune desktop Linux for instance, for performance. Definitely it's possible. And it's much more easier to tune it for in Yocto Linux, for instance. You can remove like systemd and other components and replace them even on your own init. It's even difficult to tune desktop Linux for the footprint, just because you don't have this granularity in the dependencies. So it's very often, if you need to install something on your desktop PC, then it will pull all bunch of dependencies which you might not need. So learning curve, I would say, is when you are using a desktop, it's for Yocto, it will be more difficult than the desktop Linux, because you don't have this knowledge of BitBake. You would have probably good knowledge of the Colcon, but there are some bits and pieces which you need to understand. But people are working on this to improve the situation and to make this entrance step much more easy. And then if you look at the for instance, software provenance and security updates, and you have all of this in Yocto Linux, so where you can, I think, so it's very important to look what kind of packages go in your on your system, and Yocto Linux provides very good good tools for that. It also provides SDK which you can use to develop your applications. It's apparently not applicable for the desktop Linux. So this kind of summary, yeah, I have provided, and you can imagine what the differences are. As I have mentioned, Yocto Linux is very spread across all industries, and you can see, so these are several examples where Yocto Linux is used. Is not only in robotics, but also in aerospace and defense and automotive, energy, medical telecommunications. So it's very broad acceptance of the Yocto Linux inside embedded community. Let us look at Yocto build system. I would say, based on my experience with that and with ROS2, it's pretty similar in the idea how ROS2 build system works. So there are some extensions, I would say, that ROS2 does not provide. It has a notation of layers and recipes. So layer is a collection of your packages which are combined by particular functionality. For example, you have a meta-ROS layer which contains all packages of the ROS2 distribution. And then within this package, you have various recipes for each individual package where you can describe how you would like to build this package and how you would like to then to install this package, modify this package. And you have these multiple layers which you build using Yocto build system, and one layer can supersede another layer. So you can create your layer and on top and modify all existing layers, not modify, but modify components inside the existing layers underneath. So in compare to the ROS2 build system, what it also does, it produces for you images. So you would have as the output of the as the artifacts, as the output of the build system work, you might have a different images, and you would get also application development SDK, which you can use then to develop your applications. And actually the beauty of that is that you can easily replace, for instance, machines which you generate images for. You can by like a single command replace ARM system to Intel system or RISC-V or NXP system, and then you would get absolutely the same software content, but for the different hardware. Or you could use you could add one layer and add more functionality in your image if you need, because let's assume you would deploy your image on a different robots with a different functionality, and you can easily do this with Yocto build system. So what is the difference then into development, right? So it's pretty much the same. So you would use the same tools basically, but additionally to that, you would use you would take Yocto and install it on your development PC, and you would be able to use this BitBake build tool and use, so you would still develop your package, ROS2 packages you have developed before, but you need then to create metadata for your Yocto build system, which allows Yocto then to produce artifacts, so binaries for your package. And then you would use BitBake as a build system. You would still have then GitHub Actions, then Travis or other build systems to build it. And then at the end, it will not produce like your it will not only produce binaries, but it will generate a complete image, and it will generate the image really for your particular hardware which you want to use with your robot, and it will also generate SDK, and then SDK can be used to develop applications on top. Let us see what is inside MetaROS layer. As you can see, so I have pasted here 3 windows, and first window just show that inside this MetaROS layer there are different sublayers dedicated to particular ROS2 distribution, and I'm interested into ROS2 Galactic. So, and if you see that on the in the first window at the bottom, that if I look at MetaROS Galactic, I would see a different recipes for different packages, and the so bunch of them are on the generated recipes, so they are auto-generated. If I look at the second window and look inside these auto-generated recipes, I would see then pretty much the same packages which I would see in the normal ROS distribution. So it's amend, CMake, and other RSL, CPP, and other packages. I have cat, RSL, so RSL CPP utils, and you can see that it looks pretty much, for the idea, it looks similar to the package description which you have in ROS. So basically it describes what the package name, its version, then its build dependencies, and build tool dependencies. So it's pretty much the same. And the beauty of that is all of this is auto-generated. So you basically do not need to care about to manually, create these packages. There is a tool called Superfloor inside ROS2 infrastructure, and you would use so there are, let's say, there are a lot of packages which are auto-generated, and basically you don't need to generate them for the standard ROS2 distro because they are already auto-generated for you. But if you would like to add your package to these meta layers, and I will show you how to do this, but the basic idea is that you have your, it's exactly the same if you would create a package for your ROS2 distro or add your package to the ROS2 distro. So what you're gonna do, you would need to create ROS2 package release, and which is extra to your ROS2 package, and then you put all of this information in ROS distro YAML file, and then you would use Superflow with some parameters to generate your Yocto recipe. So, and basically you're done, and then you need to copy your Yocto recipe to your MetaROS layer and then build your package. So this is pretty easy. Now we will switch to the demo, and I will show you how all this works. And I would use UR5 robot for that, which I have in my lab. And in the first part, I will demonstrate how to grab existing UR5 packages and create a small demo using existing Galactic ROS2 distribution. And then I would show how to switch from Ubuntu, which you would use as your development environment, to the Yocto base, and how to then add preemptive RT kernel for the Yocto distribution. And in compared to Intel version of the prototyping, where I would use Ubuntu running on Intel, I would also switch not only to Yocto, but also to another board, which will be a Raspberry Pi. This is the first part of the demo. I have a robot. This is UR5. And then I have a desktop PC with, where I will deploy ROS2 in the Docker container and UR5 driver, and then I will run a sample UR5 application, which will then control the robot. I have created a project which calls UR5, and what I'm basically doing, because this UR5 drivers and UR5 software is not yet part of the ROS2 distribution, I need basically to pull it or to clone it and to build it manually. And this is how I'm doing this. I just created a GitHub workflow, and I just pull a ROS2 container to build it, and I clone this repository, so UR5 repository with all dependencies, import dependencies, and then I build it, and then I create another container, which is a deployable container, where I just install all dependencies for these packages, and then I just copy the result of the previous container into this Docker container, and then I upload this container as a zip file, and it is located here. It's possible to grab it, install it as a Docker image, so you don't need to install any extra dependencies, and then run it. And now I will show you how to do that. So I have downloaded on my machine, which is connected directly to my robot, Docker container, which I have built from the previous step. Now I need to check. Here's my robot, by the way, right? So now I need to go and check in what mode it is, and it looks to me it is in the remote mode, so I can connect to it. So I just go and run this command, like ROS bring up, which UR5 bring up, which will connect to the robot. So now it is connected, and I need then to go and to put it in the my program in the play mode. So it is now running, and I can run now a demo program, and we can look what robot is doing. So for that, this is a very simple Python program, which just moves robot between 4 waypoints. And for that, I just use this container to run this program. So I just started. And voila, we see that robot is moving. And now I will do the same with my Yocto distribution. Now I will go and demonstrate how I can switch from desktop PC to Raspberry Pi. So I will use exactly the same setup, exactly the same Galactic ROS2 distribution. I will use the same sources, UR5 drivers, but I will be using Yocto instead of desktop Ubuntu. I will use ARM hardware architecture, so it's Raspberry Pi instead of Intel desktop PC, but the demo code will be exactly the same. Now, to be able to produce a Yocto image for Raspberry Pi, I have cloned this MetaROS repository, and basically you can go, if you want to do it by yourself, you can go, and there is a description how to do this on this page. So what I did actually, I have created a GitHub action which follows this description. It stores some dependencies, and then what you do basically, you just set up your Yocto environment, and then then you initialize it, and then you just go and build ROS. I have split it in two parts. So you build this ROS core first, and then with the second step, you just build the Yocto image. Here you build the Yocto image, and the only change which I did for the to build it for Raspberry Pi, as I have mentioned, so it's quite easy. I just added like this Raspberry Pi 4 machine, and it will generate me image for Raspberry Pi. If I would build it for other machine, I would need to put here other machine. What I have also did, I have just added some I have added, for instance, SSH server because it's not available by default. And then I have added some packages, extra packages, because as I have mentioned, your robot driver is not part of the default Meta-ROS distribution. And this is similar to desktop variant where I need to build it by myself because there is no packages for that. The same for ROS2 is I need to add this manually. And now let's see how this image would work on Raspberry Pi. So I have boot my Raspberry Pi, and as you can see, it's running here. And if I do like OS release, you would see that it's a robot operating system with Open Embedded Linux, Galactic, and Hardknot is their Yocto release. So it's the latest release. Now I gonna do the same. So I will go and run the same bring up command to my robot. So it starts. And then what we see here that the communication with a robot does not work. So the reason for that is that the Raspberry Pi system, which I have booted with my ROS2 drivers, is not so powerful as my desktop PC. So I need to do something about that. I need to tune it a bit. It does not work out of the box. Actually, it was a little bit surprise for me, but this is how it is. And now I will go and install a real-time kernel patch for that. So I will use exactly the same version of Yocto, but instead of normal kernel, which I have here. So it's as you can see, I have a generic kernel. I will go and boot a real-time kernel. And this is the last part of the demo. So I will go from the same setup, but what I will do, I will go and apply preempt RT patch to my kernel, and then boot the system and run the same application. And the way how I can do this is pretty simple. So I just go to the Raspberry Pi kernel recipes, to this file, to this recipe, and I just look what kind of kernel version is used, so it's 5.83, and then I go and grab actually the nearest real-time patch for that from the real-time preempt-RT website. So it's 84. And then I need, besides applying this patch, I need then to assign, to set up some parameters. And I actually copy paste exactly the same setup from the real-time working group, ROS2 real-time working group, which we use to set up a real-time kernel. And I grab the same patch and I have applied here. So it's basically 2 lines. And then what I need to do, I just need to rebuild everything. In reality, it will just rebuild the kernel and generate me a new image. And I need to deploy then this image, and let's see what happens now. I have built and boot my Yocto image again, and now it's with a real-time kernel. We see it's exactly the same relays. It's a Hark node and it's a galactic, but the difference is if I run like uname -a, we would see that now it's preempt-RT, and it is configured for the preempt-RT. So now what I would do is I just go and start my robot. So I will do then the bring up, and let's see what's happened. So now it works smoothly. It just discovered that there is a real-time support, and it's set a thread 299, and now I can go and can control my robot. So I just try to stop it, and then I just try to start it again, and it works. And then I run the same demo. So, and hopefully it will work again. So you see it starts working, and so it shows that how easy you can switch from desktop Linux to your embedded Linux and tune your system so you get like less resources, and you still have a possibility to, and then you need to tune your system, and this you can obviously do quite easy with Yocto Linux. And here's the conclusion. So after what we have seen, ROS2 provides a rich, flourishing ecosystem for robotic development. It allows a fast prototyping, doing your native development of your robotic application. And from other side, so Yocto Embedded Linux allows you tune your ROS system for performance and footprint for your particular hardware. And Yocto commercial variants provides other necessary components such as software provenance. You can check what is inside your software distribution, security scanning, CV, bug fixing support, and much more. Then here's I have prepared a couple of references which I have used through my presentation. Please try it out and provide me feedback. Thank you very much for your time. Listen to me, and we come now to a Q&A session. Thank you.
Thanks, Andre. That was a great session. Thank you for taking the time to take us through what it means to tune ROS2 for commercial use. At this time, we want to switch over to Q&A like Andre mentioned. And let's start off with the first question. And what it says here is can you remind us again, what hardware platforms are supported by Meta ROS? And which ones would you recommend we start with?
Yeah, I think currently there are basically two platforms supported and verified. It's Raspberry Pi and generic Intel. But as I have mentioned, Yocto itself supports a vast list of other platforms like NVIDIA, NXP, Freescale, RISC-V, whatever. So it's possible to compile Meta ROS or ROS2 using Meta ROS for many platforms.
Fantastic, thank you, Andre. We have a couple actually that have come in. The next one is, I couldn't catch the reason why the initial Yocto configuration didn't work on the Raspberry Pi. What was the problem that the preempt RT patch solved? Right.
In the first part of the demo, I have shown how it runs on Intel platform, and they have pretty powerful desktop PC. And then, like, I don't remember how many cores it has, and RAM and so on. And then I have moved to Raspberry Pi, and Raspberry Pi has only 4 cores. And yeah, so my version has, I think, 4 gigabyte RAM. And this is this comes like you move your stuff from a powerful machine to the machine with some kind of restrictions, right? And without real-time tuning, so it does not work, because like other tasks are running, and the communication is a real-time communication. And if you don't tune system for the real time on this particular small machine, then the communication does not work properly, and you really need to apply this real-time patch that and this example then, as I have shown, just increase the task to priority to the real time while communicating with the robot.
Thanks, Andre. The next question here is, what's the benefit of doing this with Wind River Linux versus any other Linux distribution?
I think it's also always a consideration, like whether you develop something or roll your own Linux distro, or you rely on existing commercial providers. So we do have like more than I think almost 15 years, yes, now experience with Yocto, and Yocto was actually created by Wind River and Intel Yocto project. So we know what we are doing, and we have successfully deployments over years in multiple industries. So these are the.
Excellent, thank you. And then also, do you have a recommended development environment?
Well, this, I mean, I have posted a couple of, you can take like, depending on what you want to demonstrate. If you want to repeat my exercise, I have posted the links with the project. So all projects on GitHub, and it's possible to consume them. If you want to test something different, then you might probably go and grab this original Meta ROS distribution and try it out. I think it's definitely worth to do that, just to gather some experience and compare a desktop Linux versus embedded Linux, and it's good to listen to people, but try it out, it's even better.
Excellent. And Andre, we have one more question here. And I just want to remind everyone, if there's any burning questions that you have, please do utilize the Zoom Q&A tool, and we can get to your questions accordingly. But this last question here that I have, it says, is it possible to have an on-site customer evaluation or demo of what you showed during the talk?
Yeah, sure. I mean, it's possible to try it out by yourself, just downloading just to follow my steps, which I have described. And it's also definitely possible to ask for the for the on-site evaluation. Yeah, absolutely.
All right, fantastic.
I
One
think
more
we
did
have-
come in.
have
One more
another
came in.
question.
Yeah, we got one more, Andre. It says, what is your experience in using ROS2, maybe in combination with Yocto in safety critical applications in terms of reliability? Is it mature enough? And what the individual was saying, such as like for use in autonomous vehicles or drone applications?
Mhm. Well, we do have examples that people use ROS2 for autonomous vehicles and for other, let's say, autonomous machines. In agriculture is very very spread. So there is a ROS industrial community, a strong ROS industrial community. When you safety certified, you definitely go and look at the system as a whole, and then you split and decompose your safety elements. I have seen that several companies already certified ROS2 for safety in automotive. But it's not so, I would say it's not so straightforward process as any certification, I would say.
Okay, with that, Andre, thank you for an excellent presentation and for sharing with us how to tune ROS2 for commercial use. And audience, thank you for the great questions. And just as we close out, this will be available on demand for later viewing and for you to share with your colleagues. Thank you for your time.
Thank you very much.